In this next video tutorial, I'm going to talk about how to normalize floating point binary numbers. Now the reason we do that is to increase accuracy of the number. That's the number of significant places that can be represented with usable values. So let's have a look at these three numbers that we've got in front of us. We have three different mantisses and three different exponents. So you would think they're all using a 4-bit mantissa and a 4-bit exponent. But if we say work these out, let's do the first one. So we've got 0.001 and we can see the exponent is 4. So if we float it 4 places, 1, 2, 3, 4, we then have the number 2. Okay, so we've got the number 2 for the first one. Let's do the second one then. So that one is 0.010. Okay, so what we've got is on that one we can float it 3. So we go 1, 2, 3. Now look at that. That's 1 and a 2. So that number's 2 also. Now let's take the last one, 0.100, and you can see that we've got to float it 1 place. Oh, sorry, that's a mistake there. So we've got to float it 2 places. So we go 1 and 2. And we have the number, decimal point goes there, that's 1 and 2, so they're all 2. So all these numbers up here equal the number 2. Now the point of normalisation is to stop that occurring. So one of the things that we've got to realise is that we must only have one way of representing a number in any given size of mantissa or exponent. In this case a 4-bit mantissa and a 4-bit exponent. So what we've got to do is have a rule of normalisation. And the rule of normalisation for a positive number is that all positive numbers start with a 0 after the decimal point and have a 1 before the decimal point. Now it can have then any number, in this case 2 more places that can have a value. Now look at this representation of number 2 up here. There is no more room to put any more values there. So we could in fact represent maybe 3.5 with this number, but we can't represent any more than or any less than or any more than 2 in that one. So we've lost accuracy. So whenever you're presented with a number which has leading zeros, we always float the point until the number is normalised. So let's get rid of these and I'll show you how to normalise that number so it represents the right form. So you can see that represents 2, but it's unnormalised because it isn't in the state of 0, 1. So what we do is we float the point 1, 2 places. That leaves us with the number 0.1, and because we've got 2 more zeros left, we now have moved the decimal point 2 places. So we take 2 off of the exponent, which gives us, and now we have the normalised version of 2. We can find that out. 1, 2, 1 and 2. So that is 2. So this is the normalised version of the correct floating point number. Okay, you have to remember that. Now we turn over and we deal with normalised negative numbers. Now negative numbers always start with a 1 and then numbers after the decimal point. So let's have a look at these numbers. Now you've probably worked out already they're all going to equal something very similar. So let's have a look at the first one. Now the decimal point in this case is floated 4 times. 1, 2, 3, 4. Okay, so the number we are now looking at is 0, 1, 1, 1, 1. So that will be 1, 2, 4, 8 and 16. So if we take 8 from that leaves 8, 4 from that, from 8 leaves 4, 2 from that leaves -2. Now remember that number, because now I want you to look at the bottom number there. So we agree that that equals -2, but now let's do this number here. Now in this case, this has been the exponent is much smaller, so we only move it 1 place to there. So what we have is this number here. Okay, the decimal place would be after that, and you could have as many as you want, but we have 1 and -2 because it's a 2 complements number. So again, we get -2. So each one of these equals -2. So it stands to reason that these extra ones here are getting in the way of accuracy. And by moving the decimal point out, we shift. We never get rid of the number, the significant bit here, because that always has to be a 1. But what we do is every time we decrease the place value or the value of the exponent from 4 to 3, we shift away one of the ones. And we do it the same here. We're down to 2, we shift another one away, and we're down to 1, and we shift the last one away. So that means then that the normalised version of a negative number always must start with a 1, and the next value would be a 0. And then you can have as many 1s after that as you like. But that is the rule of normalisation. These are all normalised negative numbers because they all start with a 1 and after the decimal point have a 0. These are all normalised positive numbers because they start with a 0 and after the decimal point there's a 1. So that's a normalised positive number and that is a normalised negative number.